In the middle of a global pandemic, a ragtag group of welders, heavy machine operators, and builders were brought together. They were given plans for a mysterious structure. With little information on what exactly they were building, their only clue was scrawled across the top of their plans. SpinLaunch, a space catapult. In this exclusive, behind-the-scenes documentary, I talked to the people behind this new innovative company. SpinLaunch is attempting to subvert a problem that plagues the space industry: the rocket equation. The rocket equation has been the tyrant engineers have feuded with from the dawn of the space age. A simple equation that describes how much fuel a rocket needs to carry a payload to its destination. The tyranny of this equation is that the fuel needed to deliver that payload is a payload itself, a compounding problem that makes rockets more fuel than rocket. Typical rockets are more than 90% fuel. SpinLaunch is trying to change that paradigm by imparting as much velocity as possible to the payload on the ground, eliminating as much fuel as possible from the rocket's weight, while greatly reducing the size and complexity of the non-reusable components. Their plan: to spin a small rocket in a centrifugal mass accelerator under a vacuum up to an astonishing speed before releasing it, punching through the thickest layers of our atmosphere at hypersonic speeds, gaining 72 kilometers of altitude off nothing but pure kinetic energy, before splitting its fairings and unveiling a substantially miniaturized two-stage rocket to continue its journey into orbit. You may question the numbers here, but this isn't the first time this has been done. Project HARP, standing for High Altitude Research Project, managed to get a projectile to 180 kilometers of altitude with a high-powered gun. They achieved a muzzle velocity nearly identical to SpinLaunch's planned launch velocity. However, scaling a kinetic energy launch system up to launch a 10-ton projectile needs SpinLaunch's technology. Of course, all of this is easier said than done. The challenge facing SpinLaunch's engineers is immense. This endeavor demands several new key enabling technologies.
So in terms of key enabling technologies, carbon fiber certainly takes center stage.
That's David Wren, SpinLaunch's VP of Technology. I spoke with him on the SpinLaunch factory floor about the carbon fiber reinforced plastic that they are using for their tether.
In terms of its strength to weight ratio, it's essentially unmatched by any other material on Earth. And the amazing thing is that it's actually available in industrial quantities now, and the engineering tools and simulation methods exist to really quickly iterate and understand what a composite structure will do. And then we have structures and test rigs like this to validate in the real world that the components actually fail at the expected loads. So just to give you a sense of the strength of carbon fiber, this is a pultrusion. So this is made by taking carbon fiber tow, essentially spools of carbon fiber, and pulling it through a heated die with a resin bath. Basically, the resin gets impregnated into the carbon fiber tow as it gets pulled through the heated die. And you get these really nice, highly unidirectional structures that can be used for spin launch, right? And so as small as this cross section is, right? I think this is about 1/8 of an inch thick and only a few inches wide. This can do just under 250,000 pounds of total load capacity, which is really, really impressive.
I'm trying to convert it to metric in my head. It's like, oh yeah, no, that's a lot.
Yeah, I think it's like 1,000,000 newtons or something like that. Yeah. So, and then if you look at, this is where it gets interesting is can you build really, thick cross sections of carbon fiber? You can see there's really great.
Is this pultruded as well?
So this is not pultruded. This is laid up and then it's cured in an autoclave.
Okay.
So this is essentially a subsection of the laminate that you would see at the root of the tether on the suborbital system.
So this is like.
This is not unidirectional or pultruded. But if you were to take this same cross section here and basically make this a pultruded fiber. If you just stack up multiple protruded sections, you would get about 9 million pounds of total load capacity through this cross section. So it's impressively strong for what it is.
I mean, it's heavier than you'd expect. Like holding a carbon fiber brick. I don't think I've never seen an application where that much carbon fiber has been laid up.
It's rare to see carbon fiber this thick. Yeah.
It really is rare. The final fully scaled tether for SpinLaunch's orbital system is likely going to be the single strongest tensile structure on Earth. Let's do the math on that. SpinLaunch aims to yeet its aeroshell containing the miniaturized rocket system at about Mach 6. That's roughly 2 kilometers per second. With a radius of 45 meters, the tether will need to spin 450 times per minute to attain that velocity. At that rate, the G-loading on the tether will be 10,000 Gs, meaning this aeroshell is going to exert a force 10,000 times greater than its weight due to gravity. The aeroshell with the payload and rocket is going to weigh approximately 10 metric tons. So that means the tether at the tip is going to need to be able to support 100,000 metric tons, or 100 million kilograms. To put that in context, a fully loaded Falcon 9 weighs about 0.55 million kilograms. So this tether is going to need to support the equivalent weight of 182 Falcon 9s. This is going to require a hefty piece of carbon composite with a cross-sectional area of at least 0.23 meters squared. That explains the brick of carbon fiber we saw. That brick could support 4.1 million kilograms. So the full-scale tether will need to be 24.4 times this size at its tip, but that's just the tip. This equation tells us why carbon fiber is so vital to this endeavor, because each section of the tether has to support the section above it. Its strength-to-weight ratio needs to be exceptional. If we calculate the tether area near the hub for the same carbon composite, the tether only needs to increase in area by 2.5 times, at about 0.56 meters squared. We would, of course, need to add a safety factor of at least 1.5, increasing these dimensions by 50%. I have skimmed over this equation here, but if you want to learn more about the engineering of this system and energy of getting to space in general, I've created an entire course on Brilliant to partner this video, and you can sign up for it with the link in the description. That design is perfectly feasible and is reflected in SpinLaunch's renders. We even have the manufacturing skills necessary to build even larger composite structures thanks to the wind industry. So, this is all well and good, but spinning a carbon fiber composite up to Mach 6 isn't possible in air. The aerodynamic heating would destroy it. So, to solve this issue, SpinLaunch created a massive vacuum chamber around its tether.
There's a bunch of things at the beginning of SpinLaunch that were non-starters for a lot of people, like even just building the large diameter vacuum chamber. People were telling us, the one behind me here would cost, tens of millions of dollars to build, and we ended up doing it. We had this really, really kind of scrappy, lean mindset, and we ended up doing it for, less than a couple $1 million with, about 10 people, right? Which is unheard of. There's some large industrial vacuum chambers out there, but there's quite a few of the really large chambers that are in the world are for aerospace applications, and so they're achieving extremely high levels of not only vacuum but cleanliness, right? And so the cost is proportional to that, and it's kind of exponential. They're achieving vacuums that are on the order of 10 to the negative 8 millibar torr. Typically we're operating at about 1 million times, worse than that.
SpinLaunch is breaking new ground with this kind of vacuum chamber. Typical large volume vacuum chambers, like the world's largest one at Space Power Facility in Sandusky, Ohio, are designed to simulate the vacuum of space. Those require an extremely low pressure vacuum with tight tolerances and control of contamination. They even need specialized tools like lamps to simulate the radiation and heat emanating from the sun, and cryogenic cooling to simulate the heat of space. The people that built these facilities are the industrial experts SpinLaunch had to draw from, and most thought they would never be able to build a vacuum chamber this large on their budget. But SpinLaunch does have some things on their side. They didn't need that extreme of a vacuum, as their goal is not to simulate the vacuum of space. Their goal is to minimize drag and the power required to overcome it, minimize the aerodynamic heating that would destroy the tether, and eliminate all those pesky aerodynamic effects like flutter. That means SpinLaunch could use cheaper materials like mild steel, where ultra-high vacuum chambers need more expensive specialized processed materials to avoid outgassing, where gases within the metal in the form of oxides or simply dissolved within the metal are released into the vacuum. It also makes the process of drawing a vacuum much easier. Drawing a vacuum isn't as simple as just turning on a pump and leaving it on long enough. The more air you draw out, the harder it becomes, as you are not only working against a continually growing pressure gradient, but statistical probability. The first stage of drawing a vacuum is to remove the bulk gas. At this stage, the gas is a viscous fluid, and the molecules within the chamber interact with each other often. Here, we can use traditional fluid flow pumps, like a positive displacement pump, that mechanically move molecules out of the chamber, and higher pressure air at the back of the chamber forces more air to fill the space created, allowing more air to be pumped out. But as gas is removed from the chamber, the distance between the molecules increases. This is called the mean free path, the distance a molecule can travel without colliding with another molecule. Now, pressure is really just molecules colliding, and as collisions become more infrequent, the pressure gradients that are needed to achieve equilibrium begin to vanish. Meaning, it takes longer and longer for equilibrium to be established, and the rate the pump can remove molecules lowers, as there are simply fewer and fewer molecules near the pump to remove. At some point, viscous flow stops entirely, and we enter a flow regime called molecular flow, where the distance between collisions is actually larger than the internal dimensions of the vacuum chamber, meaning the molecules are statistically more likely to just bounce around inside the chamber with nothing forcing them towards the exit. At this stage, it is impossible to actively pump the molecules out. The molecular pumps needed for this flow regime instead act like some kind of Venus flytrap, waiting for a molecule to enter it, and then its job is to prevent the molecule from returning to the original chamber. Turbomolecular pumps are basically multiple levels of turbines that knock molecules in one direction and prevent them from traveling backwards. These pumps require insane rotation speeds, anywhere from 36,000 RPM to 72,000 RPM, and need incredibly tight tolerances too. They are trying to pump individual molecules after all. So it goes without saying, these kinds of pumps are expensive. All the while, outgassing and other leaks are actively working against a game of pure chance. Creating a high vacuum requires extreme precision in manufacturing and design. SpinLaunch didn't need any of this. Mark Sipperly, the director of engineering at SpinLaunch, walked me through the vacuum pump station at the New Mexico site.
Here in the vacuum plant, the most familiar thing would be the tube that came out of the chamber and then runs underground is this manifold. So this is the very end of it. So off of this vacuum manifold, we then have a series of 3 different types of pumps. Up on top, we first have roughing pumps, which pull the atmosphere from like 1 atmosphere down to about 30 millibar. Those are dry screw pumps. They're essentially like overlapping lobes. It's one form of like a turbocharger. Then the next stage is we have this roots pump, which is like another shape of a turbocharger. It's the rotating twin screw pumps. All right, so that kicks on at about 30 millibar. All right, so it's mostly only effective 30 millibar and below. But you'll notice that each pump, it exhausts into a pump that's a slightly higher pressure, all right? So this roots pump only works at 30 millibar and below, but it can't exhaust that all the way out to 1 atmosphere, so then it's backed by another pistons pump. And then once we get down below 1 millibar, then we're gonna turn on these vapor diffusion pumps, which only are really effective down at the very low pressure, and those work like oil jets. So you vaporize oil, you shoot it down a series of channels, and it grabs onto the air molecules, runs them down a series of tubes, and then you have these cooling loops that will then condense out the oil, and then the air progressively makes its way through like a long path, and then eventually it gets to a roots pump, which can grab onto it, and then that goes to a piston pump, and then all the way out. So we talked before, vacuum may not be the best description, because most people think of vacuum as like a hard vacuum, like, in torr is what most people are used to, like e to the -7 torr, so like 6 zeros and then the number. That's like true vacuum, that's hard vacuum, that's where you test like electrical propulsion systems and like high-end space features. That is nowhere near the atmosphere that we need, and that vacuum is also really expensive to get to, and you have to follow a lot of stringent rules, like you can't use steels, you have to use aluminums or like thin coatings. Even like putting your fingerprint in a vacuum that low would take like weeks to boil off. We only require the equivalent of like to the -3 torr, all right, so 0.01 millibar or 0.1 millibar. Today we're going to be running it like 1 millibar because we only pull the vacuum that we need because vacuum is expensive. It's closer to describe it as like a high atmospheric chamber than a vacuum chamber specifically.
This is another one of those technical issues that the internet made a big deal out of without fully understanding what SpinLaunch actually needed out of the vacuum chamber. One of the other primary concerns expressed on the internet was the tricky and unique problem of a vehicle traveling at hypersonic speeds from a vacuum into a thick sea-level atmosphere. To begin with, we need to prevent air from rushing into the vacuum chamber once the vehicle is released. SpinLaunch is aiming to be a high-frequency launch system, capable of launching multiple satellites per day, holding the vacuum between launches to decrease energy and time costs. However, the primary concern is the disastrous effects that air would have as it meets the tether spinning at hypersonic speeds. This would be an incredibly expensive single-shot system if this was allowed to happen. To solve this problem, SpinLaunch needed a way of sealing the chamber extremely quickly after launch. So, inside this long tube attached to the vacuum chamber is a double-door airlock with doors on either end of the tube. This tube is also under vacuum during spin-up. As the vehicle is released, using a release mechanism that SpinLaunch kept hidden from our cameras throughout the shoot, it passes into the exit tunnel, where the first door rapidly closes behind it. As this first door is closing, the second door will begin to open. The atmosphere will begin rushing into the tube and give the Aeroshell its first taste of the hypersonic flight regime it will be flying in. The first and second door need to close quickly enough to prevent air from entering the vacuum chamber. This is not an easy problem. Millisecond delays that may seem trivial in most cases start to mount up when the vehicle travels this quickly. The time it takes for an electrical signal to propagate, the time it takes to overcome the inertia of the door, the time it takes for a proper seal to form. All these problems become matters of survival at these speeds. Once again, SpinLaunch are keeping their cards close to their chests on this one, but they did give me a demonstration of the door closing in their factory and engineering hub in Long Beach, California.
Well, it's moving really fast, and so when the without specifying, you can do a countdown.
Yep. So whenever you're ready for a countdown, just let me know.
Yeah. So basically, what's going to happen is, this is going to be filled with a, for lack of a better word, like a black door, which basically you'll see that like you can pass through this with a vehicle, and then in an instant it's going to be closed.
Okay.
So and again, it's like faster than the blink of an eye. So you'll see a little bit of settling after it closes, but it's basically 95% closed within 30 milliseconds.
Oh wow. Okay.
Closing airlock in 5, 4, 3, 2, 1.
It's pretty fast.
Yeah, that's not what I was expecting.
Yeah, it's fast.
So it actually closes, like it's actually hinged.
There's a pivot, yeah.
Okay. Yeah, I wasn't sure if it was going to be a sliding thing, but the hinged one makes sense as well. Yeah, that wasn't what I was expecting.
So it's 100% reusable. Basically, you can set that back up again and do it again and again and again. So that's a key aspect of it, is that you don't have any major consumables in the process. So
that's cool.
Yeah, it's fast. Visceral.
All right.
I don't know.
It's a door closing. I don't know what to ask.
It's really important not to let air back in. So that's why I have it.
Oh, everybody jumps.
So the airlock is a really critical subsystem of the overall architecture. As you travel from vacuum into the atmosphere, because the tether is still rotating at high velocities, you want to maintain the vacuum inside of the vacuum chamber. And so the airlock is your first line of defense for that. And so we have multiple redundant airlocks, just like what you see here, that the vehicle passes through and it subsequently closes behind the vehicle, preventing the air from inrushing and re-entering into the vacuum chamber. So the exit tunnel is really the only portion of the chamber that experiences a rise in pressure.
I imagine that allows you to reset and increase frequency of launches as well if you're not having to reestablish.
Yeah, totally. So you can do you can essentially provide an airlocked space for the end of the tether as well, and so you can basically just repressurize that space as you load in new vehicles. It's possible you could do vehicle integration in vacuum, but currently we're anticipating actually repressuring a small portion of interfacing around the tether, repressurizing a small portion and integrating the vehicle without it being in vacuum.
How many launches a day do you think you can manage? I think that's one of the advantages of this, that you can.
Yeah, I think on the very high end it's upwards of 10. I think on the low end it's about 5 is a pretty good nominal target for us. We see viability there.
In SpinLaunch's public videos, the secondary airlock has simply been sheets of mylar. This is one of the few problems that becomes easier as the launcher scales. As the exit tunnel grows in length, it will take air longer to reach the door at the base of the exit tunnel. SpinLaunch have only just begun these 1/3 scale tests, with their fastest launch to date at 1.6 Mach, slowly ramping up the speed of launch as they test their systems. This prototype launcher features some other simplifications compared to their final planned configuration. One of the most obvious problems to tackle is the issue of vibration. When a spinning object's weight is not evenly distributed, it will vibrate. This is how rumble feedback works in gaming controllers, a simple electric motor with an uneven weight attached. However, with a structure as large as SpinLaunch's tether, spinning several times per second, any imbalance could shake the entire structure to the ground. This is a major problem, because, by design, the tether releases a 10-ton weight right at its maximum velocity. SpinLaunch needs a way to balance the tether after launch. There is a very simple solution to this problem though. Release a balanced weight from the other side of the arm at the same time. Right now, they are simply releasing a counterweight that slams into an armored section of the vacuum chamber. We saw one of these counterweights being manufactured out of fiberglass in the Long Beach factory. However, over the long term, having to clean up the mess this creates after each and every launch is far from ideal. The ideal solution would be to release a counterweight in the form of another launch vehicle after a single half rotation of the tether. The oil-filled journal bearing the massive axle sits upon should be able to absorb the force of this imbalance over a period of time this short. The next issue we need to concern ourselves with is the aeroshell punching into the atmosphere at Mach 6. This, again, is a fairly unique problem. Typically, weight is a restraining factor in aerospace, but for SpinLaunch, the energy required to spin the aeroshell up to speed is actually rather trivial.
It's on the order, I like to use the analogy of like a Tesla, right? So the Tesla Model S Plaid is about 0.7 megawatts. So on the low end, it's about 100 Teslas, but it really comes down.
Is that for the full scale?
Yeah, for the full scale, yeah. For the orbital system, you're talking about like on the low end, on the very low end, it's probably about 65 to 70 megawatts. And again, that really depends on where you end up with the final orbital tether, whether or not what safety factor you operate with, what tether strength you end up with, your effective, tether, cross-sectional strength. That all feeds back into itself, and then you have to, kind of scale it accordingly. I would say, like, really conservatively, like, if you wanted to spin up really fast, then you're talking about a higher power demand. So whether you want to spin up in an hour or 2 hours, proportionally makes a difference of how much power that you need. But on the high end, you're talking about maybe 150 megawatts of power, which is like, I don't know, maybe in layman terms it sounds significant, but you can there's motor catalogs where you purchase, the motor that has that capacity, right? And so this is, it's industrial scale hardware, and certainly, mostly off the shelf.
Do you need to worry about like grid integration at all when you're suddenly drawing that much power?
No, I mean, for better for worse, no, because you're typically, particularly for early, orbital accelerators that we're building, we're expecting them to be in really remote locations, kind of remote coastal locations, greenfield sites that don't have substantial existing on-site, resources or power. So you're basically, bringing your own power, and so you have to, decide on, what is your energy source? Are you doing energy recapture, et cetera?
SpinLaunch claims their total energy demand per spin-up is about 100 megawatt hours. The cost per kilowatt hour for industrial facilities is about 6 cents. So that's a cost of $6,000 in electricity cost. That's insanely cheap. To put that into perspective, 100 megawatt hours is equivalent to about 9,600 litres of kerosene, about 8 tons of fuel. For reference, the Electron rocket from New Zealand's small satellite launching company Rocket Lab, capable of launching a similar sized satellite, weighs a total of 12.5 tons. The vast majority of that weight being its own fuel and oxidizer. SpinLaunch claims their rockets will need to carry about 30% of the fuel and oxidizer compared to their competitors. They are essentially replacing the first stage of a traditional rocket with an easily reusable kinetic launch system. SpinLaunch will also be able to recapture a good deal of the electricity stored as kinetic energy in the tether using regenerative braking, even further reducing their electricity bill. Because of all this, the limiting factor for SpinLaunch in terms of weight is actually the weight the tether can support, and as a result, it actually makes sense to maximize the density of the aeroshell, because it affects a variable that will drastically improve its ability to punch through the atmosphere, its ballistic coefficient. Ballistic coefficient is essentially an object's ability to resist air resistance. Think about how hard it is to throw a feather. No matter how hard you throw it, it's not going to go very far. It's got a large surface area for air resistance to act upon relative to its weight. That's a low ballistic coefficient. Ballistic coefficient is found by dividing the mass of the projectile by the drag coefficient multiplied by the cross-sectional area. So, SpinLaunch effectively wants to maximize the mass relative to the cross-sectional area. This is obviously not typical for aerospace vehicles.
Yeah, if you look at re-entry capsules, whether it's for something like the Stardust return capsule where it's really, really high velocity, or you look at re-entry from orbit for a manned capsule or something like the space shuttle, they're typically using thermal protection systems that are extremely low density, like on the order of less than 300 kilograms per cubic meter. It's just basically foam. And so typically that means you're making like significant compromises, like the material often is brittle or prone to fracture, or really expensive, or gets worn away, and then you have to replace the tiles, kind of in the infamous case of the space shuttle. So what we're dealing with is, you're on the tip of the vehicle, you have materials like copper, which not only are they a significantly higher density, right? You're talking about thousands of kilograms per cubic meter, but they also have really great thermal conductivity. So you can basically, as you transition through the atmosphere, you have a high heat load, but then you're dumping that basically into heavy dense materials that have good thermal conductivity.
This is one of those unintuitive consequences of this style of launch. When I first saw the full-scale aeroshell on the SpinLaunch factory floor, I first asked if I could ride it like a cowboy, but then immediately noticed the bimetallic nose cone. I knew from looking at it that it was made from copper and aluminium, and that struck me as extremely odd. Those metals would melt at the temperatures I associate with hypersonic speeds. But because SpinLaunch launches at Mach 6, it actually transitions through the lower atmosphere rather quickly, and as a result, the heat generated can simply be absorbed by these large heat sinks. Aluminium and copper's high thermal conductivity means the heat is distributed through the body of the aeroshell before it has a chance to damage the vehicle. The hefty carbon fiber shell is also incredibly strong. SpinLaunch has already pulled their smaller scale aeroshells out of the ground, buried several feet deep from the force of impact, and reused them with minimal refurbishment. With a parachute, these aeroshells will be fully reusable with minimal maintenance, especially as they serve no function other than to protect the inner rocket stages. This isn't an intricate mechanical machine. Launching from the ground at these speeds comes with advantages too. If we plot drag coefficient versus Mach number for a bullet-like projectile, something rather unintuitive occurs. The drag coefficient rises as you would expect until we hit Mach 1. At this point, it starts to fall as Mach numbers increase. This is the equation for drag. It's proportional to drag coefficient, air density, and velocity squared. With drag coefficient being lower at hypersonic speeds, it actually makes some sense to punch through the thick lower atmosphere where the high-density air causes drag to rise as fast as possible. Deceleration is a function of time after all. Meters per second squared, meters per second lost per second. Let's calculate the dynamic pressure this drag would create at launch and the deceleration it would cause. The dynamic pressure is found by multiplying air density by the velocity squared and dividing by 2. At sea level, at Mach 6, the dynamic pressure will be about 2.6 megapascals. The final aeroshell is 1 meter in diameter and has a drag coefficient of about 0.1, which means the force applied to the aeroshell at launch will be 205 kilonewtons. This sounds like a lot, but here's where ballistic coefficient comes in. The drag force is being applied to a 10-ton body moving at Mach 6. That's a lot of inertia. Force equals mass by acceleration. Acceleration equals force divided by mass. That means high mass equals less deceleration. In this case, deceleration due to drag will be about 19.8 meters per second at launch. But it will rapidly decrease as we move through to thinner and thinner layers of the atmosphere and lose velocity. In fact, with SpinLaunch's planned trajectory, we can plot the atmospheric density the aeroshell will encounter over time, halving in just 5 seconds and dropping to less than 10% of the original air density in 15 seconds, while gravity will remain more or less constant at 9.8 meters per second. That means gravity losses form the majority of energy losses in our transition to orbit. In total, SpinLaunch will lose about 150 meters per second of velocity to drag and 1,000 meters per second to gravity. Satellites like Starlink orbit at 500 kilometers with a velocity of about 7,700 meters per second. So, even if SpinLaunch maintained their 250 meter per second velocity from launch up until the aeroshell broke apart, the two-stage rocket motor hidden within would still have its work cut out for it. However, now free from the mass of the aeroshell, the substantially miniaturized rocket needs only a fraction of the mass of fuel and oxidizer to rapidly accelerate the 200 kilogram satellite, the largest satellite the system can launch, through the thin atmosphere at this altitude. We can actually graph the relative velocity of the spacecraft over time, starting at Mach 6 at launch and ending up at 1,500 meters per second when the aeroshell splits apart. The rocket motors then kick in to rapidly accelerate the satellite to its 7,700 meter per second orbital velocity. The physics here absolutely check out, but whether the economics and cost of development will be viable is the big question to be answered. SpinLaunch has built a 1/3 scale prototype at a relatively low cost, but the hardest part of this technology is scale. They have reached 1.6 Mach thus far, have tested their satellite components at 10,000 G in their test facility in Long Beach, and are continually upping their test parameters, pushing further and further. This is a comparison of SpaceX and SpinLaunch's proposed launch trajectory, but it doesn't tell the full story of the real driving issue here: economics. A SpaceX launch to low Earth orbit costs about $67 million. The heaviest Falcon 9 payload to date has been 16,250 kilograms on a densely packed Starlink mission. That equates to a launch price of about $4,100 per kilogram. However, small satellite launch companies like Rocket Lab, who offer greater control over orbit and launch schedules, charge about $15,000 to $25,000 per kilogram. Dollars per kilogram is not a perfect metric, but gives us some idea of the competition SpinLaunch is facing. SpinLaunch's main competitive advantage is in the decrease of expendable materials like fuel, while substantially miniaturizing rocket components. They also have huge potential to launch far more frequently than their competitors, helping the economics of scale to kick in. SpinLaunch claims to be targeting an ambitious per-launch price in the range of $500,000, placing them at $2,500 per kilogram. In my time in SpinLaunch, talking to their engineers, it's clear they are excited and believe in this company. The basic napkin physics of SpinLaunch absolutely check out, and they are well on their way of solving the engineering challenges. But scaling up this monstrous engineering effort is going to require enormous amounts of investment, and SpinLaunch could not disclose the answer to many of my questions as they seek patents for their solutions. I got little info on one of the most difficult parts of the launch system, the release mechanism for the Aeroshell. Even the 3D models SpinLaunch provided for this video had the release mechanism removed, so we had to model our own along with the internal rocket structure. The design of the satellites is another problem, due to the massive Gs the satellites have to survive. But G-hardening isn't as large an engineering challenge as the internet seems to think.
The most difficult part, so besides the structures, is also the reaction wheel. So the reaction wheel generates momentum and basically steers the bus. And so it typically is a big mass that's cantilevered up at a certain angle, which is the one thing that we don't like. You don't want having a big mass sticking up on a cantilever.
This is what I assumed was going to be like a difficult thing to, because it inherently has to be fairly high mass to control the satellites.
Right. And so we've done a lot of work to, instead of re-engineering the wheel itself and figuring out different ways to do that, we basically just took a clever way of deploying the wheel. So we support the wheel in the flat orientation, and so when it's spinning, it's well supported. The bearings are unloaded, and so it can spin and do its thing. And then we deploy the wheel for when it actually needs to operate. So it's a simple solution for what could have been a really difficult problem.
And does the axis of the actual wheel cause any issues when it's like being G-loaded? I imagine that it's like a fairly high weight to have on an axle. Yeah,
so what we do is we unload the bearings, and as part of the deployment mechanism, we reload the wheel into the bearings.
Oh, okay, so it's just taken off completely.
Again, trying to make simple solutions for very difficult problems. Yeah.
And like that, those are very simple answers to I figured that the inertial wheels would be difficult, and it's like then you just think about it, it's like, oh yeah, that's actually a fairly easy thing to just not deal with. You don't have to have it in the exact configuration when you launch. And the same with the solar panels, you can have them, like as you said, loaded.
Yeah. So it's the problems aren't necessarily hard to deal with. It's just you have to think differently. And so it's not that these are difficult problems, we just have to change the way we think about designing satellites a little bit. It's not a lot. The nice part is, too, that over the last 60 years, what people have been trying to do with satellites actually has helped us, because they want to reduce mass, they want to make things stronger. So every bit that they're forcing them to deal with shock and vibe already helps us, and it already inherently starts to make them more G-hardened. Most components, we don't have to do anything to them. Maybe a little epoxy here. But one of the most surprising events that we had here amongst the entire team is we took a board that had a capacitor stuck up, maybe a quarter of an inch. And we all looked at it and were like, okay, that thing's just gonna fly off and hit the wall. And we spun it and we brought it back and it just went, burp, and that was it. And we all like, all right, our intuition is completely changing, and it's because it's so little mass and it's being held on by two pieces of steel. The amount of force that was really imparting on those two pieces of steel was relatively small. So it just bent over, and we all kind of like, oh yeah, after you think about it, it does make sense. Okay, yeah, it does survive. So our intuition is starting to grow about, yeah, this little connector that's sticking up really isn't that big of a deal. And so that has been, in a positive way, very surprising, which is great.
Gs can only create force where there is mass, and it turns out the satellite industry has been finding ways to reduce mass for decades. A simple aluminium can is capable of withstanding 10,000 Gs with a basic redesign of its structure. Minimizing weight located on unsupported surfaces lowers the mass available to be multiplied by the Gs. and some simple corrugation can help the aluminium absorb some of the loading without buckling. We spun up an off-the-shelf star tracking camera using SpinLaunch's in-house centrifugal accelerator, which can already achieve 10,000 Gs, and the camera worked perfectly fine just moments later. This is a really interesting engineering challenge that I think the internet is giving a hard time for some bizarre reason. Posing questions about basic physics calculations without actually doing the math and then saying it's impossible. Even missing the fact that kinetic energy launch systems have already reached beyond the Kármán line 6 decades ago. If you want to check the math and physics of this problem yourself, instead of taking my word for it, I have, in partnership with Brilliant, created an entire course deep diving into this problem, starting with an in-depth interactive lesson on the physics of orbit and traditional rocket launches, and moving on through to interactive calculations of the launch speeds a kinetic launch system like this would need to achieve, and the design considerations for the tether itself. This is your chance to test your understanding of the things you learned in this video with a curated, interactive course, all designed with fun, interactive, real engineering blueprints. You can get access to that course right now and all of Brilliant's other curated interactive courses by clicking the link in the description. You can get started for free, but the first 500 people to do so will get 20% off Brilliant's annual premium subscription. With that, you can level up your STEM skills, no matter your experience, or develop your scientific thinking. With courses on computer science fundamentals, statistics, and algorithm fundamentals, you can kickstart a career in coding with their curated courses. Brilliant has been the longest-running partnership on this channel. Starting in 2017, they have funded nearly 40% of the videos on this channel. This is a major milestone in both of our journeys, creating in-depth lessons together to test and deepen the knowledge you learn in our videos. A natural partnership where we can help each other fulfill our mission of inspiring and educating the next generation of scientists and engineers. If you're looking for something else to watch right now, you could watch our last video on the life-limiting challenges facing the next generation of spacesuits, or you could watch Real Science's new video on the strange phenomenon of deep-sea gigantism.